academics and industry study groups. And they've been running every year since 2015, with the exception of this year due to COVID. And so the idea is that we get four to six challenges from industry. Throughout the years, we've had various industries. We've always had Fonterra. We have other industries like Fisher and Paykel, Zespri, Transpower, and various others. And so these companies bring a problem they're facing, and we spend 5 days trying to solve this problem, or at least understand it a little bit. And I say 5 days in quotes here, because really the first day is trying to understand what's going on. And the last day is really just presenting your work. So in actual fact, there's probably only about 2.5 of those 5 days that we spend working on these problems. But despite the relatively short amount of time that we can spend on these problems, we often make really big leaps in our understanding of the problems and can make quite significant improvements to these processes that these industries are bringing to us. And so the point is that academics and students from many disciplines work together in a team to find solutions. And I think this is a really great way to do mathematics, especially interdisciplinary science, is that we're all sitting in the same room, coming from a whole bunch of different angles, different thought processes, and all working towards the same goal. And I think this is something that people who are involved in VTS may be interested in contributing to. So I'll talk about that a little bit more later. But for now, I just wanted to bring you the problem that I worked on in 2016, which again was from Fonterra. Can we predict the shelf life of milk powder, especially in elevated temperatures and humidities? So as I said, working in a team, and this was the team, so quite a large team. So we have a mix of students and well, employed academics. So Steve Taylor was the other moderator. So Steve is a mathematician at Auckland University. You'll see Graham Wake's name there. Clive Davies is a chemical engineer. Andrew Fowler is a mathematical modeler from Ireland. John Main Dolan is a statistician, and Richard Clark is an engineer at the University of Auckland, and various other people too. And many of these were students, by the way, so either master's students or PhD students, but often we get bachelor's students as well coming along to these things. The one thing I would say too about MINS is that every time I've gone there, I've learned something new. Often a piece of mathematics, often a piece of statistics as well, and often something to do with other areas of science. So it's a really great way to continue learning. Okay, so Fonterra, I think everybody knows Fonterra, but they maintain a very vast list of products that they sell in New Zealand and around the world. And so one of their major exports is actually milk powder. And so the life cycle of milk powder, well, we start up the top here on the, hopefully you can see what's on my screen, my cursor, but it starts here on the farm, right? So one of the great things about New Zealand is that we have pastures that cows can graze on. We're not feeding them too much extra feed. It's mostly grass fed. And so that ensures that we get a really quality product. And so, okay, so we get cows, we send them to the milking sheds in the middle here. They get milked and the milk gets put on tankers. The tankers take the milk to the factories. The factories do some chemical engineering processing on this milk. I think they mostly use a spray dryer to convert this liquid milk into milk powder, which they export in various ways. So sometimes they'll export it in bags. So this kind of packaging in bags. Sometimes they'll export it in metal tins as well. You've probably seen baby formula comes usually in this metal tin type arrangement. But they get exported in these massive bulk lots around the world on container ships. So from the time it's turned into milk powder to the time it's put on a ship and arrived halfway around the world can be quite some time. And then it does allow some potential for the milk powder to change its structure during that time, just through the aging process. So there are so many factors affecting the shelf life of milk powder. The raw ingredients themselves, the product formulation, moisture, water activity, vitamin levels, type of fat, the storage conditions, the packaging, because the different types of packaging allows different amounts of moisture and oxygen through. And basically, there are just a lot of factors that can affect how long a batch of milk powder is going to last. But four of the major factors are the storage temperature and humidity, the amount of air or oxygen that is within the product, and the amount of light that the product gets exposed to. So we had this thing in New Zealand a few years ago where they started making milk bottles that let no light in, and apparently that makes the milk last longer. I couldn't tell the difference though in taste. So here's an experiment that Fonterra ran where they have different batches of the same milk powder, but just dried out to different levels. So AW here is water activity, which you can sort of think of as the amount of water. The higher that number is, the more moisture there is in the gas, which is surrounding the particles. And so you can see that in the middle here, where you have the lowest number of water, so 0.26 water activity, you get this lovely fine powder that looks like a powder should. But as soon as you start increasing that water activity, the amount of water in the gas phase, then you start getting clumping. So on the left, you have something that's slightly higher water activity. You can see well, some of it's powder and some of it's clumping. And on the far right, there are a lot of lumps. And well, it doesn't really mix into your coffee very well, right? The other thing that, apart from clumping, the other thing that can happen is if the temperature and the humidity is large enough, you can get something called Maillard browning. And so this is really good if you are cooking a steak, because you want some Maillard browning when you're cooking a steak, but it's not so good if you're sending milk powder or baby formula around the world. So there's nothing unsafe about having the Maillard reaction in a lot of powder, but it can change the flavor profile. And of course, if you were looking at this, you would probably prefer to drink the one on the left. You may not, if you saw the one on the right, you may think it's bad and not drink it. It's still safe to drink though, is the point. It just, it's more of a consumer satisfaction issue. Oh, I should say that these are actually from the same batch. So the one on the left is a batch that was kept in New Zealand, so in the New Zealand climate, and the one on the right is one that was sent to the Maldives, which of course is hot and humid compared to New Zealand anyway. Okay, and so like I said, there are multiple different packaging options when Fonterra sends products out. So on the far right here, we have this sort of bagging. I'd say cardboard, but there is of course other layers in there as well, such as plastics, thin layers of plastic in the packaging material. In the middle here, you have a blue milk powder, which is basically all stored in thicker plastic there. And then you have on the left the metal tin, which more of us are familiar with in New Zealand in the form of baby powder, right? Or yeah, baby milk powder. But the packaging basically affects the rate at which oxygen can diffuse through the packaging, the rate at which water vapor can diffuse through the packaging, and other physical factors, such as the strength. You don't want a packaging that's going to break on as it's being transited. Okay, so Fonterra, so we have these different options for packaging, but Fonterra ran some experiments themselves, and they basically varied the initial water content, so the percentage of water content along the x-axis here. They varied the storage temperature on the y-axis here, and just observed what happened. So after 1 week, so this is after, every image here is after 1 week, you can see the high temperature and the high water content milk powders had significant Maillard browning. The lower storage temperatures were still okay, but again, there was significant clumping at the larger water contents. But in the next slide is time after 1 year. And you can see, well, I really don't think anybody would want to drink milk powder that was sort of 65 degrees after 1 year. Well, your milk would look an unusual color. But you can see that, you know, the three main things that affect the quality or the Maillard reaction in milk powder are the initial water content or the water content, the storage temperature, and time. So those three things are the three main factors that seem to affect the shelf life of this milk powder. And so that's what we decided to focus on at MINS, was the water content, the storage temperature, and the time. Okay. So one of the first things that our group did was map the complaints that Fonterra had. So Fonterra keeps a list of complaints from around the world. And obviously Fonterra products get sent to almost every country around the world. And you can see from this map that they do get complaints from all around the world, various climates from New Zealand all the way through to Canada and everywhere in between. But of course, the amount of product that Fonterra sends to these countries varies significantly. So if we normalize this data by the orders that they get from these countries, then it tells quite a different story. So the complaints that they get from, for example, Canada and New Zealand are really few compared to the amount of product they send to those countries. The points that stand out as being complaints which are significant compared to the number of orders are all in this sort of equatorial region. So in other words, in all the hot, humid countries, this is where we're getting sort of an excess number of complaints, or let's say more than we get in New Zealand and cooler climate countries. So again, this gave us confidence that, at least for a simple model, one that we could make some progress on during the 1 week of the study group, was to focus on basically temperature, humidity, and time. So we made some assumptions in our model. So these are, I guess, not exhaustive assumptions, but they are some of the assumptions we made. We assume that the amount of moisture in the bag increases only due to permeation through the bag membrane. So in other words, moisture in the atmosphere can permeate through the bag, and that's the only way that moisture in the bag can increase. Okay, the rate of diffusion of water vapor through the headspace and the powder. So the headspace is just, if you have a bag of powder, it's just the air gap at the top of the bag. But the rate of diffusion of water vapor through the headspace and powder is much larger than the rate through the bag membrane, which was reasonable when we did the calculations. So we just treated the bag as a bulk lot. We didn't model any spatial structure or any transients of diffusion of moisture throughout the bag, okay? Because it just took a lot longer for the moisture to get through the bag membrane than it did for the moisture to permeate throughout the bag once it was inside. So all of the water entering the bag via permeation increases the water activity. There is no moisture in the air in the bag headspace. There's no, well, sometimes, you know, these foods undergo chemical reactions. Sometimes those chemical reactions can release chemically bound water, but we're just going to assume that that is minimal compared to the amount of water that's entering through the bag surface. The temperature of the powder in the bag is taken to be equal to the ambient temperature, and we ignore the rapid transients and thermal conduction. So John Bronland here at Massey University and Tony Patterson did some work in this regard, and they actually showed that the transients and thermal conductions were fairly small. So we felt that was safe to ignore that. We're only modeling a single bag of powder, so when Fonterra export these bags or this milk powder, they often put them in big stacks, right? So massive stacks, massive containers. This is probably the assumption that we need to ease or do some more work on in the future, and that is that work is being planned at the moment, in fact. We're ignoring chemical reactions which occur slowly but will be important for long-time predictions of powder quality. So this is another future area for research where instead of just modeling the moisture, we can actually model the chemical reactions that are occurring in these milk powders. But again, we'll leave that for future research for now. I'm going to skip 8 for the minute and go to 9. So permeation proceeds at steady state and is uniform over the packaging surface area. The bag permeability is independent of ambient conditions, and the bulk density and structure of the powder is uniform. Okay, I just want to circle back to number 8 here. So lactose crystallization, this is a chemical reaction that occurs in milk powder. It basically starts this degradation of the milk powder. Basically, once we start getting lactose crystallization, we'll start getting that Maillard browning that is undesirable. Okay, so we're saying that this begins once the temperature of the powder, which is TP, exceeds the glass transition temperature, TG, for the current value of water activity, AW, in the bag. So I have a plot here, which is some data on various kinds of milk powders, which is plotting what's called the glass transition temperature. Okay, what that glass transition temperature is if we go above this glass transition temperature, then we start to get a change in the structure of the powder. We start to get this lactose crystallization and this Maillard browning. And so this glass transition temperature depends on the amount of water in your bag, right? Or in your powder. So for a low water activity, let's say of 0.1, the glass transition temperature is roughly 60 degrees. But once you get up to, water activities of 0.5, you're at 5 degrees or something. So if we keep our bag of powder below this glass transition temperature, then it will last a lot longer than if we peak above this this glass transition temperature. So this is really the main point of our model is we want to know when will a given bag of powder exceed this glass transition temperature. Okay, and that can happen in 2 ways, right? We can increase the temperature of the powder, so we can move vertically on this graph. So if we increase the temperature of the powder, we can exceed the glass transition temperature, or we can increase the amount of water in the bag and move horizontally on this graph and cross the line just by increasing the amount of water. Okay, so looking at a bag of powder now, we're basically modeling the transport of water, of H2O gas, over the bag, what do we call this? The outer surface of the bag, the packaging, right, basically. Okay, so basically we have some simplified model where on the left of this picture here, we have the atmospheric conditions. In sort of this bluey green thing in the middle here, we have diffusion through this bag membrane. And then on the right-hand side is the water molecules absorbing into their milk powder. Okay, so the main component of this, of the physics here, is the diffusion through the bag. The absorption and desorption through Henry's law is relatively rapid. The thing that takes a long time for this type of material is diffusion. Okay, so we can write down a model of diffusion. And so this model again was from a Massey University thesis from Jacques Kruger. And this is effectively a simplified model of the diffusion equation, the diffusion of water vapor through the bag membrane. Okay, so d by dt of MH2O, MH2O is the mass of water in the bag. So the rate of change of the mass of water entering the bag is equal to the permeability P divided by the thickness of the packaging. So the permeability is the permeability of the packaging. A here is the area, packaging surface area. And then we have a differential of pressure, right? So the atmospheric partial pressure of water minus the partial pressure of water in the bag. And so that pressure differential is what's driving the diffusion of water through that packaging membrane. Okay. So now these two partial pressures, we can write these like so. So P0 here is the saturated vapor pressure, or saturated partial pressure of water. RH is the humidity of the atmosphere, or the relative humidity of the atmosphere. And AW is this thing called water activity, which is a measure of how much water is in the milk powder. Okay. So we have some values of permeability of the packaging. So 8.1 times 10 to the negative 12. This was a value that we got from the packaging manufacturer. Well, we didn't have a better option, so we went with that number. I would probably like for Fonterra to actually measure that, because I guess you can't always trust what's on the tin. The thickness of the packaging was about 75 microns. That's about right. The packaging surface area was, well, for a standard bag of milk powder, was 1.4 meters squared. Of course, things like the relative humidity of the atmosphere is dependent on where you're storing the powder. And the water activity, well, Fonterra reduces this by drying out their milk powders, right, using the spray dryer. So they can actually alter the water activity here by drying out the milk powder more. They can reduce that water activity. Okay. Well, we have an expression for the saturation vapor pressure of water. Well, this is just some empirical law, but a fairly well accepted one. And the point here is that, well, if P0H2O, the saturation pressure of water increases, then so does the amount of moisture that gets through the bag. As the temperature increases, so does the amount of moisture that will get through the bag. As the differential between the relative humidity and the water activity increases, so does the amount of water that will enter the bag. Okay, and well, there's an expression relating X, which is the ratio of mass of water to the mass of solids in the bag, to the water pressure, to the water activity, but this is just a subtle detail. The point is that we can solve this first order nonlinear differential equation numerically to try and understand what is going on. Okay, so the key parameters really are the permeability, the thickness of the packaging, and the packaging surface area. So Fonterra can control this, right? They could buy a bag which has a higher permeability, or sorry, I mean a lower permeability, which would reduce the amount of moisture that can enter the bag. Or they can make the bag thicker, which will reduce the amount of moisture that can get into the bag. Or they could reduce this packaging surface area, but well, maybe they don't want to do that. But each of these things increases costs, right? So they can make a better barrier to water entering the powder, but we don't know exactly how much difference it's going to make to their bottom line compared to the amount that they lose from having to refund customers. Well, they can also control the humidity and the temperature to some extent. So during transport, that's fairly easy to control. You can send a refrigerated boat. But for example, once you put that boat on the docks, well, anything can happen. They can have, you could leave the milk powder out in the sun, and it can actually heat up quite high. So there is some control they have over these atmospheric conditions. And again, they can reduce the water activity by drying out the powder more. But again, that means running their spray dryer for longer, which means further costs. And the question is, is it worth it really? So remember, we have this glass transition temperature curve. So what we did was solve that differential equation for a given starting condition and just measured how long it would take for our packaging or our bag of powder to cross that glass transition temperature. So the first example here is where we have a constant temperature. So we're keeping this bag of milk powder at a constant, I think it was 20 degrees Celsius and 80% relative humidity. Okay, and we started out at a water activity of 0.2. Okay, water activity is 0.2. So again, we're keeping it at a constant temperature. So really this horizontal line in blue here, this is effectively measuring time. So as time goes on, we're moving horizontally along this blue line. The red line is our, well, approximation of the glass transition curve. So as soon as this, well, as time moves on, the amount of moisture in the bag increases just by diffusion because the relative humidity is relatively high. And when this blue line meets this red line, that is when we're saying, well, now our bag is at the glass transition temperature, we can expect some degradation in the quality of the powder. And so that, for this particular setup, happened after about 686 days, so a couple of years. Not quite a couple of years. Okay, so we can run this experiment at constant temperature and constant humidity for various starting conditions, so various humidities, various temperatures, and we can plot or we can draw up a table of the shelf life for the powder. So you can see here for an initial water activity of 0.225, so down in the bottom right here, that's our initial amount of water in the bag. This is each of these numbers in the table here is the time until we hit the glass transition temperature for a given temperature, storage temperature T, and a given relative humidity RH. And you can see as soon as you start getting into the higher temperatures and the higher humidities, we actually hit that glass transition temperature relatively quickly. Okay, so just for an example here, if we have a relative humidity of 60 degrees and a temperature of 40 degrees Celsius, so this is not unusual for some of the warmer climates, then we hit that glass transition temperature after only 100 days, so a little over 3 months. And again, that was for this initial amount of moisture or this water activity of 0.225. Now, if we spend a little bit more money to dry out this powder a little bit more, and we reduce this initial starting condition to 0.175, so our initial water activity to 0.175, then for the same relative humidity and temperature, we actually get 181 days or close to 6 months until we hit that glass transition temperature. So for a slightly increase in cost, which reduces the initial amount of moisture in the powder, we actually get almost double the amount of time, storage time, which can make a big difference in some of these hotter regions, hotter climates. Okay, well, what about testing some real data? So this is somebody put a thermometer or something, or a thermocouple on a bag of powder as it traveled around the world. And on the y-axis here, we've got the measured powder temperature. And on the x-axis, we've got the time in days. So this powder lot was actually sent to, I think it was Nigeria. And you can see here that during transport, it heated up to about 37 degrees. And then you get this massive spike at about 35 days. So what happened here was that the powder was unloaded onto a dock. And again, I think it was Nigeria. And it was just sitting in the sun for days. And well, you can see it actually gets really, really hot, right? And so what we did is we ran our mathematical model with this temperature profile and the initial starting condition of the water content of 0.2, so the water activity of 0.2. Again, in red here, we have our glass transition temperature. And we just plotted when does this batch of milk powder exceed the glass transition curve. Okay, and so we can see the first time it does that is after about 36.5 days, this first point here. It then ducks below that point until later on it actually goes above that point again. But as soon as you go above that point, you start to get this degradation in the milk powder. So it could be that even after just over a month, because of the storage temperature, that this powder is starting to break down. It's irreversible. and you could potentially expect some complaints about that batch. So we did come up with a very simple model. Again, it was only 1 week of work, so for a week I think we did really well, especially as this experience matched the experience of Fonterra's quality control staff. And so I had some feedback from Fonterra that they were using the model to explain to their customers some of the problems that the customers have been having. Okay, and we made a series of recommendations to Fonterra, and some of those are below. So we suggested that they basically do a cost-benefit analysis on, well, potentially drying out the milk powders more if that milk powder is going to be exported to warmer climates. But also you potentially could dry out that milk powder less if you're just going to keep it in New Zealand, right? Or somewhere that's temperate. Because actually the shelf life, if you're storing it at 20 degrees Celsius, is actually pretty long. Okay. Well, they could also do a cost benefit analysis on, well, changing the kind of bags that they use. They could find bags with lower permeability or thicker membranes. And of course, we have future work with them that we'd like to perform, developing models to have a look at some of these spatial and temporal variations in temperature and moisture, especially with the way that the bags are stored in big mass pallets. Okay. So how does this relate to VTS? Well, that's a good question. Well, there are actually quite a lot of industrial transport and logistics problems, which I think would really be beneficial to work with VTS and mathematical modelers and industry. For example, in the same year that this Fonterra problem came up, there was a challenge from Zespri predicting fruit quality in the supply chain from harvest to market. And so there are a lot of you know, similar problems that Zespri was facing. They of course have some other kind of chemical reactions, these kiwi fruit release gases during transport. But again, I think that these kind of problems would be really helped having experts in sensing technologies, in fact. So our simple model gives an understanding of when ambient conditions can negatively affect this powder. But really practically, we need a way to monitor the current state of the transported products and potentially even communication between batches of products, you know, which I think is something that VTS, it's natural to you guys. So what can we do going forward? And, well, we can talk to industry, and I think engineers are much better at talking to industry than mathematicians are, so we are still learning. You can talk to your mathematician friends because, well, the applied mathematicians in New Zealand, we love to get involved with projects that can be interdisciplinary science and move both mathematics and science forward. And I'd like to extend the invitation to people from VTS and anybody that you might know who's interested to come to MINS, because I think the more expertise and the more experience we have, the better. And I promise it is fun. Attendance is free as well. I should point that out for academics and students. MINS 2020 was supposed to be held in Canterbury this year, but of course it got cancelled due to COVID. But it will be held in Canterbury in 2021, assuming we have COVID under control. So I'd like to thank you for your time and listening to my talk. This is just a lovely picture of my university here in the Manawatu with a classic Manawatu grey sky day. And I'm happy to take any questions.
Okay, thanks, Luke. Really appreciate it, and especially thanks you added the links, you know, to our VTIs, and especially I think for, you know, when I discuss the topic, you know, I invite Luke to offer us VTIs, and we have several topics, but I think this probably is the most related because basically, if you look at the vehicle technology, we can use that as a sensor. It's not just for the air conclusion. Actually, they can have inside the sensors for the temperature and humidity. Yeah. But now I like to pass time to the participants. So any of you have questions? We don't have many people, so we have a small group. But on the other hand, we have the opportunity. You know, just feel free, just you know, unmute your microphone, and you can raise your questions. For example, like you know, Brent.
Yes.
Yep.
Yeah. Very good talk, Luke. I think you described a complex situation very simply, and clearly, which is a very good skill. I think you're right about the sensing for a lot of these applications. Routinely, does Fonterra actually measure the temperature, time history of their transport of their milk powder or not? And how do they do that? Just out of curiosity.
Yeah, so I'm not actually sure exactly how they do it, but I know that back in 2016 when we were working on this, that they were having problems with their powders that were going to these warmer climates. So that's why they sent that temperature trace to the African batch, which I presented. I don't know. I haven't followed up with them to see what they're doing at the moment. But I mean, I know it's something that they're very interested in, and I think it's not unique to Fonterra. It's any basically food export from New Zealand is going to be having similar problems, right?
Yeah, I think it's the, again, there's a cost trade-off there as well, and she being able to have cheap sensors that are either in the container or in the bag or something, right? So there's a challenge with respect to cost there too, of course. But yeah, thank you.
Thanks, Brent.
Yeah.
Oh, thanks, Brent. Yep. So I just I actually sent a message. Just feel free, unmute, and also, you can, if you like, you can show your videos, and it's more casual discussions. So any question from Nate or Carrie? I see you join us. It's also from our school's mathematics department. Carrie or Nate? Any questions from you too?
Can you hear me? That's the question.
Yes. Yeah, I can hear you. Yeah, I can hear you. Yeah.
That's good. I just want to say, Luke, that was really well presented, and like Brent said, you broke it down to be something that was really easy, and we could our audience could follow you through with it. It was really good, really well done for presentation skills.
Thanks,
I don't have any specific questions. I know that I've worked with Luke with a Fonterra problem. 2011, years and years ago.
Okay.
And what we also do at the MINS too is we also extend invitations to the secondary school maths teachers as well, so they actually get a chance to get in there and have a chance at getting in and seeing how maths and other sciences can be used to solve a real problem as part of their PD, and then they can hopefully take that back and somehow incorporate in their teaching. So you did a really nice presentation, Luke, and really good. And I'm really interested to see how this goes forward, and I'm more than happy to jump in at any point in time.
Okay.
Thanks, Carrie.
Yes, thanks, Carrie. Yeah, thanks, Carrie. How about Nate? Would you like to say something?
I have a question. I'm from chemical and material engineering University of Auckland, and working with the brand very closely. I have a question. You show a very nice example. You build the model is kind of from first principle. So we usually call it a white box approach. But for some process or problem is quite complex. Maybe the simple the first principle model maybe is impossible. So usually we will call another one called a black box, or we use some people call machine learning like a method. So any comments on do thinking any comments application about machine learning technology for your
Yeah, machine learning. So I'm definitely not an expert in machine learning, but well, I don't know. I guess that.
But if you said the mathematical model, do you also including machine learning technology, or you just want pure from the first principle?
Yeah. So I mostly work from first principles models because that's just what I know and what I'm relatively capable of. But machine learning is something that's extremely interesting, of course. But I personally would need somebody to hold my hand.
I guess as a follow-up to that, I'd maybe are you aware of any regression models or time series models, for example, that people have developed in this area?
I'm not aware of them. They probably exist, but I'm not aware of them myself.
But I think the machine learning actually you really need the data. That's is really sometimes it's hard. Even if you look at Luke's work, the data actually they can collect actually is from complaint. They don't really have the mass of data about all this temperature, humidity, during the delivery. But that is something maybe in the future, this vehicle have the sensors can help. But so far, I think that machine learning is beautiful. I think even like deep learning, but it really need intensive data. You can actually build the model on the data. But if you don't have the data, I think the traditional analytical modeling are still probably the mainstream ways to do that.
Yeah. So as I said, we had quite a big group working on this problem in 2016. And so part of the group was some statisticians, and they basically came up with a suggestion or a recommendation to Fonterra to do a series of testing of controlled environments, controlled humidity, temperatures over longer periods of time, and taking more samples. Well, sometimes they just take one samples over a year. So they were suggesting taking more samples more regularly. And so potentially over time, when Fonterra develops this capability, they could generate some data that maybe is useful for some of these machine learning models.
Yep.
Actually, can I ask another question? I'll just put my video on. In terms of, so you mentioned before that Fonterra might also have been interested in, I guess, reaction engineering approaches. I guess you were mentioning, of course, the importance of lactose crystallization. Are you aware of them pursuing those aspects at all? Or,
so I'm not sure how far they've got with it because, well, we've done about 3 other projects with Fonterra, totally separate since this one.
Mm-hmm.
So we've been thinking in other ways, but actually Steve Taylor, who was one of the moderators, and I have talked about trying to get a student to work on both the spatial modeling of moisture through these bags and also the chemical reactions of which there are many during a powder's lifetime. But yeah, that's something we're definitely really keen to pursue.
Yeah, okay. Thank you.
And also, look, I'm quite interested on this Mint workshop you mentioned. So basically, is academics from different area. You have this like 1 week. It's like you have this casual discussions, or you have some themes, and to trigger the discussions. So how it usually works is.
Yeah, so usually there are some companies that have very specific problems or very specific questions, and the more specific, the better it works, in fact. And so they're basically on day one, they come and present their problem or their question to everybody.
Yeah.
And then everybody can decide which problem they want to work on. And so we separate into these groups and discuss possible ways forward. We ask a lot of questions because we never understand everything on the first day.
Yeah.
Or even the last day, really. But we ask a lot of questions anyway.
Yeah.
And just try to understand, get a handle on the problem, get some ideas of where we could go forward. And then the next 3 days are basically just pursuing those ideas. Some of them work out, some of them don't.
Yeah.
And in the end of the day, you have some set of results that hopefully answer the question the company was looking to answer.
Yeah. Okay, I see. Yep. So any questions from? Yep. Oh, you need to unmute. I can see you need to unmute. It's mute. Yeah.
Yeah. Hi. Thank you, Luke. I enjoyed that, and I missed Men's 2016, so I missed that one. So I just wondered, is there much? You know how you can also buy yogurt powder as well as milk powder, and I suppose the only difference really is that the yogurt powder's got some dried bacteria in it. Have you ever looked at, is there any difference? Does anybody look at the difference between those, or has anybody looked at that?
It'd be a good next step, wouldn't it? Yeah. I think there's 2 things, right? That lactose crystallization curve, would be different for yogurt.
Yeah.
But also, as you say, you've got sometimes the live bacteria, which adds another
dimension to your modeling.
Exactly. Yeah.
Might be an interesting one to look at. Yeah.
Yeah, a delicious one. Yes, absolutely. Yeah.
Actually, it's very quite inspiring because it's about the food. You know, for example, at the very beginning, I talked to Luke, like even the meat, you know, and the seafood, because these are probably more sensitive. Yeah. And even actually, when Luke talk, I look at the milk powder, you know, at my home. Actually, it's before I didn't really, you know, have the attention on these temperature things, but now I have to pay attention. Yeah. And even, you know, when delivered to the customer, like usually sometimes I just you know, drink it during the night. I think it's really just in the open air. You know, the humidity, you know, sometimes in West is quite high, so I should be careful. Yeah, thanks for that.
That's right. You definitely want to keep it sealed as best you can.
Yeah.
I should point out too that when they bag this powder, they don't just leave the powder in air. They put a lance inside the bag and pump it full of nitrogen and maybe some other gas too, just to try and reduce the amount of oxidization.
Yeah.
We didn't go into modeling the oxidization in this one, but yeah, it does matter if you leave the bag open. Yeah, for sure.
Yeah. Just should be careful. Yeah. And even I'm thinking like maybe in the future, if the technology can, you know, really cheap enough, maybe in each bag they can have you know, like RFID or small sensor inside. But again, you know, it's come back to can you actually reuse these bags, because it still has a cost for that. But yeah, it is really to our life. Should be careful. Yeah. But actually, it's a lot of experience, you know, from the ICT part as well. Yeah. So any questions from Nate? You like to say something? No.
I also
yeah, please.
About the bag, if I think the bag is inside they have the nitrogen, they pump nitrogen inside the bag, yeah. But okay, yeah. About diffusion driven by the concentration, not by the pressure, yeah. Or bag pressure should be sometimes can be higher than outside, yeah. If you get hotter, is that one will change some diffusion driving force on?
Yeah, so we made the assumption that the temperature of the atmosphere was the same as in the bag, so that sort of transient was quite short. So then the thing that was driving the water itself was the partial pressure on the outside and the partial pressure on the inside, on either side of the bag membrane. Yeah, so it was just driven by basically a pressure differential.
Yeah.
Okay. Yep. Okay, so I think the time is nearly like 1 hour. So, and also I like to thank Luke because he just recovered from a little bit cold, and yeah, really appreciate for that. And also I already see the interest, you know, for your slides and also for the record video. And if you like, you know, like the video and the slides, I think you can you know, write an email to Luke directly, and you can see his name and you can find his contact. But for the video, if you like one, you can just send me an email. So I'm really happy to share this. You know, it's also through our VTI's public channels, and I hope it's help, you know, to your works. Yep. So thank you so much for that, and I wish you have a nice Friday afternoon and also a relaxed weekend. I just hope, you know, our Auckland can low down to level 1. We can move around, because basically we had a plan to visit Luke in Macy, but just disrupted by this COVID-19. And also I'm really looking forward to visit Luke like maybe at the end of the year if the alert level is down, or the next year in the mint. I really interested to go there to have a look. Yep. Okay. Thank you. Thanks.
Thank you very much, Luke. Thanks,
There we go. Thanks, Luke. That was great.
Thanks, Luke.
Excellent.
Thanks, Carrie. Yeah.
Bye, everyone.
So, bye.
Bye. Have a good afternoon. Good Friday.
Yeah. I was gonna just going to ask Luke quickly, that was the way you presented that was just lovely. It was really easy,
Yeah.
and
Yeah,
I'm wondering whether or not you are happy if I can, I'll email you, I'll talk to you a bit later about it, about showing that to a class at a secondary school, high school, bits of it, about the processing that
Yeah.
you went
Yes,
through.
sure.
Like you started off, you're quite happy for that? Yeah. And I thought you
course.
did a wonderful job of just outlaying
Yeah,
how
yeah, very
things
nice.
happen without
It's-
making it too,
yeah, yeah.
there was some wording with the assumptions, but that's to be expected because everything's got its special language. But I thought you did a wonderful job about setting that out for a
Yeah, yeah.
general audience.
Yeah.
Did
Cool.
really well.
Thanks, Gary.
And also
Yeah.
connect math with science. I think it will be really attractive. And otherwise, a lot of students or they think, oh, the science math is a little bit hard. But when they connect science, I think the interest can really boom people's interest, because the math is
Yeah.
the most beautiful language. It can describe
Yeah.
the problems.
Yeah.
Okay. Thanks.
Cool.
Thanks to you
you.
guys. Have a nice weekend.
Thanks,
Yep.
everyone.
Yep.
Ka
See ya.
kite anō.
Okay.
Very good. Yeah, no, really nice, Luke. Thank you.
Thanks,
Yeah.
Gary.
Thanks, Carrie.
Everything's good. Everything's good in Massey.
We're still here. We're still cooking. We're still
Yeah,
teaching. We're still
that's good.
researching. That's good.
That's good. That's good. Yeah.
All we
Okay.
can ask
Good.
for, yeah.
Yeah.
Good. Anyway, go well. Have a good weekend.
Okay.
Bye, Gary.
Bye.
You too.
Bye.
Yeah.
Bye.
Yeah.
Thanks, Will. Thanks
Okay.
for
Thanks.
inviting me to give this talk.
Yeah. Yeah. So do you mind actually? You can send me the slides. And
Absolutely.
yeah, and then just in case some of them, is contact me. And also when the video is ready, I can send you the link. Yeah.
Absolutely. So
I think maybe at the beginning I missed a little bit because I need to ask the hoster, but later on I ask the writer of hoster, so I can probably I start recording from when you're talking the topic, but at the beginning part a little bit missed. Yeah. But
no
when you
problem.
got slides should help. Yep. I was really appreciate it, and yeah, have a good recovery, drink some water. Okay.
Thanks, Will.
See ya.
I look forward to seeing you soon.
Sure,
Okay.
sure, definitely, yeah.
Okay.
Oh,
Bye.
and also if you have this mint brochure, I think you can send me. I can share with the people around me. Yep.
Yep. Awesome.
Okay. Have a nice afternoon.
Thanks, Will.
Yep. Bye. Yep.
See you, mate.
Yep.